how many people?
I think we have
Yeah,
15
we're all
people.
looking in what happens when there can be changes to rules and
Well, I'm sorry.
All right, let's get started here. Hopefully we'll get through some beam bending today, and we're going to start with bending stress associated with shear. All right, glad some of you decided to make it today. Friday must have just been a rough day, huh? Rough day. I get it. I get it. What's that? Yeah, there's a homework and a quiz this week. Okay. Homework is due, was it Friday? Yeah. And then the quiz I'm opening up on Thursday at noon. It'll be open through Monday at midnight. Okay. So just in case you don't want to do it over the weekend. And it might help to have the homework back too. So, all right. So a little recap of Friday. We started talking about this idea of having multiple materials in a cross section, right? Up until this point, we were calculating our moments of inertia, right? Associated with this cross section that was made up, say, all of steel or all of wood, right? It was made up of discrete, say, areas, like we did here in this example. Holy fuck, we did a lot of stuff, didn't we? This I shape, right? We broke it into more manageable pieces so that we could come up with an overall moment of inertia. Okay, well then we talked about how this gets a little bit, it muddies the water a little bit when you start looking at now, instead of having this block entirely of steel, maybe one of those blocks is made out of wood, okay? And so in order to maintain strain, we decided that we couldn't change the way that the strain was distributed across the cross-section based on this radius of curvature, right? So we have strain that starts at 0 at the neutral axis, and it goes to a maximum, say, at one end of our cross-section and minimum at the other. And if we were to add depth to this member, you're going to start screwing up the way that that strain behaves, right? We're going to have more distance, which means we're going to have more strain. And so in order to come up with an equivalent system, we decided that we couldn't add depth. And so what we end up doing is just making, right, one material into the other material based on a ratio of our moduli of elasticity, right? Modulus of elasticities. Came up with this N ratio, right, which is the original modulus of elasticity to our reference modulus of elasticity. Essentially our original material over what material are we trying to change this into, so we have one uniform material across the entire cross-section. And then once we have that ratio, we can use that ratio to adjust the stresses, but before we do that, we use it to adjust our centroid, because we're going to change the areas of our section, and then the centroid changes, our moment of inertia changes, right? So essentially the same thing as what we did before, except we're just going to make our materials wider to account for the fact that they are different in stiffness, E, right? So for wood and steel, for instance, if we're going to take steel and make it into wood, obviously steel is a lot stiffer than wood, so we're going to have a big number for N, and we're going to make whatever steel in our cross-section really wide, right? You could do it the other way, and if you had wood and steel, you could take the wood and make it steel, right? But then now that wood's going to get really, really narrow. Same thing.
Okay, but we're keeping what we're changing the same thickness.
Yep, so we just changed the width. Okay. And it all came back to some of the stuff we discussed on Friday, but we don't need to repeat it, so. Okay. So in this case, we have a wood beam. This happens fairly often. I've done this in design, okay, where you have maybe an existing structure, maybe it's a residential building, okay, or a commercial building made out of wood, right? It's wood frame. In order to get more capacity out of these wood members, we will slap a steel plate on the bottom of that wood beam, okay? Screw it off, and we'll talk about shear flow and how you calculate how many screws and what the spacing of those screws would be, or if you glued it on, what the glue adhesion would need to be. Let's say we glue it on there, okay, or screw it on there adequately enough that this system acts compositely, and we do that to beef up the beam, right? We change the use of the building, we add another story, whatever, we do something different, and it adds to the demands on this beam, so we need to straighten it. So So we add the steel plate. They give us that the elastic modulus of the wood is 12.5 gigapascals and steel is 200 gigapascals. Again, like I said, big difference between the two. The allowable bending stresses of the wood and steel are 7 megapascals for wood and 150 for steel, okay? And they want us to tell them what is the largest moment that can be applied to the beam, okay? So we decide that we're gonna reinforce it. We reinforce it with this beam or this steel plate. What quantity of moment, right? What demand can we put on this beam now? Well, as we've mentioned, we need a equivalent system, right? We need one cross section that's all made up of the same material. So in order to do that, step one is develop our equivalent system. Okay? That all hinges on this modulus ratio, right? N, which we know that modulus ratio is the original over the reference. We could go either way, right? We could make this whole cross-section into wood. We could make this whole cross-section into steel. I'm gonna make this whole cross-section into wood, okay? Essentially make the area of steel larger to account for the fact that steel's a lot stiffer. But you could do the other way and you could take the wood beam and make it into a steel beam as well, okay? So I'm gonna say the original is my steel, right? Because I'm going to transform it into my reference material, which I'm gonna say is the wood. We get an N of 200, right, gigapascals over 12.5 gigapascals. Or we get an N ratio of 16. Right? All that's really saying is that steel is 16 times as stiff as wood. Okay? So now we need to make ourselves a new cross section. So this is what our new cross section is going to look like, right? Might actually delete this thing. I'm going to put some coordinate axes here, okay? Because once we've transformed our cross-section into one material, we're going to need to figure out a centroid, right? So we know that we couldn't affect the depth. So this D, which is 380 millimeters plus 20 millimeters, or 400 millimeters tall, that's how tall this whole thing is, right? Decided that we can't change the depth because it starts messing with strains. So this is 400 millimeters, okay? But we need to change the area of this steel plate, right, by 16 times. We gotta multiply it by 16. So if we're not gonna change the thickness of the steel plate, we're gonna change the width. So now we've got 160 millimeters, which is our original width, right? The steel plate. We're gonna multiply it by 16 and get 2,500 millimeters. So this is what our reference cross-section looks like, right? Our equivalent system. If we made this completely out of wood, we would have to make it with a piece of wood, thin piece of wood plate on the bottom, right? That's 200 or 2.5 meters wide, okay? And 20 millimeters or 2 centimeters thick, okay? To come up with the same equivalent system. So now that we have this, we need our centroid of this cross-section, right? We need the centroid, so then we can figure out the moment of inertia, and then we can figure out stresses. Y bar, we know, The equation for y bar, yeah.
Okay, I had a question just about the area thing. So the n value we're multiplying by is applied to the area, right?
Yes.
So we need 16 times the area.
Yep.
Okay.
Which is the same as saying, if we hold the thickness the same,
Okay.
it's the same as saying we're gonna change the width by 16.
Okay.
Right? Because we cannot change the depth. That's what's fixed. It's 400 millimeters. Okay. So now that we have this new system, then we use, or this new equivalent system, we can then determine what our centroid location is, and then also from that, our moment of inertia, right? So if we start by summation a sub I, y sub I, so we have 2,500 millimeters times 20 millimeters, that's our thickness of our steel plate, right? So that's our new area for our steel plate. Its moment arm at this point, if we're gonna have Z, right, we're gonna say Z is our reference axis for Y bar, okay? So we're gonna calculate Y bar based on that Z being our reference axis, or essentially the bottom of the steel plate. So the distance to the centroid, right, this is Y2, and that equals 20 over 2, right? 20 millimeter thick steel plates. This is 20 over 2, that's Y2. Area of the wood beam 1, right? Area of the wood beam 1 is 222 millimeters by 380 millimeters. Right, that's the height. And then our height to our centroid of that block is going to be the thickness of our steel plate, 20 millimeters, plus half the height of our wood block, right? 380 divided by 2. Divide all of that by the summation of the areas, or 2,500 times 20 plus 222 times 380. So we get a Y bar equal to 134 millimeters. I hope. Okay. So what does that mean? Well, that means the centroid of our cross section, right? This equivalent cross section is 134 millimeters. From the bottom of our cross section, okay? Make sense? So now we know that we have the centroid, we can figure out our moment of inertia, right? Because we need the moment of inertia about this centroid now of our equivalent system, which is essentially made up of two rectangles. We've done this before, so we're gonna figure this out. We're gonna say, okay, I Z bar. We have our wood block, and we have our steel block, right? Which is really transformed right now into wood. Okay. Well, we know some of the equations of interest. Right, we have IZ, which is BH cubed over 12, and we have our parallel axis theorem that says the moment of inertia about any axis is the moment of inertia about a piece's centroid plus the area of that piece times the distance of that piece's centroid to the location of our moment of inertia that we're calculating, right? So we need to know area of our wood block. Well, this is 222 times 380. This is 2,500 times 20. Moment of inertia, the centroid of each of our blocks
Let's BH cubed over 12, so 222 for the wood block is wide. It's 380 millimeters tall, divided by 12. Concrete, 2,500, that's our width, times 20 cubed over 12, right? The distance, that's the last piece of our parallel axis theorem, is the distance of our member or block to our new centroid. In this case, it's going to be for the wood block, it's going to be, 20 plus 380, 380 over 2 minus 134, right? It's essentially, our block has a
d sub I for our wood block is going to be the distance from our reference axis, right, all the way up to its centroid, which is the thickness of our plate, right, which is wood now, plus half the distance of our wood block, minus the distance to the centroid, right? That gives us our
distance from our centroid of our block to the new centroid. And then we have 134 minus 20 over 2. Well, this is d sub I
going the other way, right? We've got to figure out what's our distance from the centroid of our steel block, or now our wood block,
to the centroid of the overall system. Okay, well, that's 134 minus 20 over 2. Not going to bore you with all of the intermediate calculations, but I'll tell you that IZ bar now is IZ of the wood plus AD squared, right? This is all of the wood plus the steel plus AD squared of the steel transformed, right? In our equivalent system, and we get an IZ bar equal to 2.27 times 10 to the 9th millimeters to the 4th.
okay?
They asked us for the maximum moment, largest moment that could be applied to this beam. They gave us allowable stresses, right? It's the allowable bending stress of the wood and the beam in the steel. So we really are starting out with our bending stress equation, right? Negative my over I. Well, we're looking for our maximum moment. We're given allowable bending stress, right? We just calculated our moment of inertia, and we can figure out y, right? Y is just the distance from our centroid to our extreme fiber, right? The furthest distance to the outside of our beam, whether it's to the top or the bottom. So if we looked at our y max for the wood, well, that's going to be our total beam depth minus the distance to the centroid, right? Because this right here I don't know how well that comes out. Yeah, that's not too bad. Is Y max for the wood, right?
That is the furthest distance we have to go away from the centroid and still be in the wood, right?
Similarly, we need the max for the steel. Y max steel. Well, that's just 134, right?
And in this case, a negative, because we're going below the neutral axis, right? It's positive above, negative below. So we have negative 134. So if we rearrange our equation now, you get the moment equals moment of inertia times our allowable stress over our max distance from the neutral axis, right? We rearrange that. And that's for our original, or our transformed material, right? So if we look at wood, I'm gonna look at our wood now. Our moment of inertia, 2.27 times 10 to the 9th millimeters to the 4th, right? That's what we just calculated up above. Times our allowable stress. Well, they gave it to us as megapascals, or newtons per millimeter squared. A 7.5 is our maximum allowable stress for the wood. Divide that by 266, that's what this is, 266 millimeters. We get a moment that's maximum 64 times 10 to the 6th Newton millimeters, or 64,000 Newton meters. Okay. So that's the maximum moment that can be applied to this cross section in order to maintain a minimum bending stress in the wood of 7.5 megapascals. Okay. And right, this is negative. This is the maximum negative moment. But really, your allowable stress can be positive or negative, right? You could have a different allowable stress and tension as you can have in compression. In this case, it didn't say anything about that, so it's assumed that this value here could be positive or negative. So the allowable moment really could be positive or negative, right? We could put a positive or negative moment on our cross section and still reach this limit, right? Or be within it. So that's our wood. If we look at steel, this is our material that we switched, right? We changed it into a reference material. We changed to wood. And so our transformed section parameters affect our stresses in our wood section, right? So we actually have to bring it back and bring our stresses back to what it would be like in our real cross section. And like we talked about on Friday, in order to do this, our stress equation now becomes negative N times M times Y over I, right? And if we were to rearrange that, our moment now is our moment of inertia times our stress divided by N times Y, right? Because our real cross-section doesn't have that much area to it. But because of this change in the stiffness, because we have such a stiffness difference, it's going to move our moment of our centroid, which is going to change our moment of inertia. And so we need to take that into account when we're calculating what the wood's stress is. When we go back to the steel, because it is stiffer, we can then reduce it back again. So in this case, our maximum moment that can be applied is negative 2.27 times 10 to the 9th millimeters to the 4th. Watch your units. As always, 150 megapascals is our allowable stress in steel. Our ratio was 16, and our maximum distance from the centroid, our transformed centroid, is 134 millimeters.
So this is again, like I was saying, this stress can be positive or negative. So really the results you get can be positive or negative, right? You could put a positive moment on this cross section or a negative moment on this cross section. All it's going to change is whether or not your stress is in compression or tension. And if they don't give us a specific allowable stress in tension or compression, like concrete would be one, where it's got a lot higher allowable stress in compression than it does in tension, right? Wood's also one, but they didn't give us anything here. So 159 times 10 to the 6th Newton millimeters, or our maximum moment is plus or minus 159,000 Newton meters. Right. Well, out of these two, the wood controls, right? So we could put 64,000 Newton meters on this cross section without exceeding the allowable stress in the wood. The steel is going to be way fine, right? We can handle over double that, okay? But if you go over our 59,000, is it 59,000? 64,000, we would then fail the wood, right? Our allowable stress would be exceeded. So our answer would be 64,000. All right. We're going to talk just for a brief second about eccentric loading. One, because it's important, and two, because there is eccentric loading on the the quiz, okay, that I put out there. Very easy concept here, okay? An example of which would be a C-clamp, right? I'm sure lots of you have seen or used C-clamps, right? You clamp it down on something, you exert a compressive force, right? The twisting of the clamp exerts compression on whatever you're clamping together. Well, that compression or whatever piece or element that you're squeezing is pushing back on this clamp, right? With P, equal and opposite. So it's pushing back on this clamp P. And so if we were to cut this clamp and draw a free body diagram at say AA. So we draw a free body diagram of all the system on the left-hand side of cutting into AA. We would end up with some internal forces, right? This is a free body diagram. And these internal forces would essentially become both a axial load and a moment. Okay? We summed moments about that cut. We would have to have a resisting moment that resists this force that's headed way out here, right? Which has this moment arm 40 millimeters. So what this becomes when you have eccentric loading is a combined forces or stresses problem, where our total stress is going to be our axial stress plus our bending stress, right? We just use superposition. Similar to axial load and torsional load. Now we have axial load and some bending load. Right? So we get, I'll put this down here. So total stress, sigma x, right? Our normal stress along our x-axis is going to be our force over our area, which is our axial stress, plus our bending stress, right? Negative my over I. Done that.
So we merely just add it together. If we had a bent member, another example, we had a bent member and we were applying a tension force to it. Right? If we made a cut at point C, right? If we made a cut out here, I think everyone's in agreement, right? The applied load acts through the centroid of that cut, and we would have just an axial force, right? But the fact that we have to then take this axial load that's out here and run it through this deformed section of this member. If we took a cut at that member, right, and drew a free body diagram at the cut, we would have to have some internal moment that's resisting the fact that one of these forces is now eccentric to the cut, right? And that moment would have a magnitude of the axial force times that eccentricity, P times E. And then we would have this axial load F, right? So if we took that and zoomed in on what's going on there, right? Same thing, we've got superposition. We essentially have the axial load that creates axial stresses. We have a moment that creates bending stresses. And we add those two together. And that gives us our final stress distribution. Okay, so this is our axial. This is our bending. And this is combined. Okay, so in our case, sigma x, be F over A plus negative P times E times Y over whatever moment of inertia there is across this cross section, right? We have to see what it looks like looking on the end of it to see how it resists bending, okay? But as you can see, this is our neutral axis for bending. If we had just pure bending, neutral axis, in this case it looks like it's ending up right in the center. Well, now that we have combined loading, and we have some axial load, if we add axial load to it, the combined loading ends up moving that neutral axis, right? The point that has zero stress. That's all I really want to get you guys to get out of that. Okay. Method of superposition. So in the quiz, if I gave you a member that happened to have a force on it and an eccentricity, and I asked you, what is the stress at point C? You could draw a free body diagram at point C, figuring out what the internal forces are. And then you could go through superposition and figure out what the combined stress is at that point, right? Axial stress and bending stress. You got it, Brandon. Okay. All right. Last example. I think. Yes. Last example before we're going to jump into shear stresses in bending, okay? So in this case, again, we have a composite beam. We decided to bolt 2 wood planks on either side of a steel plate. All right, they gave us some dimensions to all of these things. They said the modulus of elasticity of wood is about 1.8 or 1800 KSI. Steel is 30,000 KSI. They say that this beam is simply supported, right? So it's got a pin on one end, a roller on the other. It says the distance is 24 feet, and then it gives you this uniform load that's applied over the middle half of the beam, right? L over 2 or 12 feet. We don't have to worry about the weight of the beam in our calculations, which is good. And they ask us to do a couple things. One is determine the maximum bending stress is produced if that uniform load was 400 pounds per foot.
And then they come back and say, well, now assume that the allowable bending stresses of the wood and steel are 1,200 psi and 24,000 psi. And then they want us to determine what's the maximum distributed load that we could put on this beam, okay? So let's figure out the stresses with a load of 400 pounds per foot, figure out what's the maximum load we can put on it given the allowable stresses, okay? So a couple different ways that you would approach it in the real world, right? A lot of times you'd check the applicability or the acceptability of a design, or you're gonna go through a design and you know what the loads are, and you're gonna figure out what the maximum load could be, okay? All right. So part A. Well, we know that we have multiple materials. We have a composite section. We need to transform our sections. So we have our governing equations, right, for stress of our reference material is negative my over I. Does not change. And then we have our original stress, right? If we're transforming it into something, we are transforming it into a reference material. When we bring it back, we're going to bring it back to our original material. That's when we take into account our ratio of modulus of elasticities. So we get this NMY over I. So really, this one's going to be our stress in the wood is our reference material, right? Whereas the stress in the steel, we need to take into account the ratio. And this is because I'm going to take the steel and make it into wood, right? If you went the other way, these would switch, right? Our reference material would be the steel, and our original would be the wood, right? Because we'd have to change the wood back to wood when it was all said and done from steel, okay? Well, before we get there, a few things we need to do. In those equations, we have N, M, Y, I, right? All of those things, we need to figure out what those are. Which means we need to transform our cross-section which means we need to do statics. Okay, which you guys love so much. That's what makes the world go round. Okay, statics. So if we look at this cross section, it's going to have some sort of shear and moment diagram, right? We've got a beam simply supported. It's got a transverse load, which is uniformly, a constant uniform load over the middle half. We know that our total length was 24 feet. So we've got 6 feet until we hit our uniform load. It's going to act over 12 feet, and then we have 6 feet to the end. We need to figure out what our reactions are. In order to figure out our reactions, I'm going to calculate what our resultant force is acting through our uniform load. Because it is a constant uniform load, that resultant acts at the centroid, right, of that uniform load. Centroid being the center. So that force that's being applied is going to be the uniform load magnitude times 12 feet, right? Magnitude times the length. Got it. Okay. If we look at our reactions, well, due to symmetry, right? You could go through in some forces in some moments, but due to symmetry, I think we all could agree because it's symmetrically loaded. The reactions on both sides are going to be half of the ultimate magnitude of our uniform load, right? The W12 over 2. Those would be our reactions. Anyone want to fight against that? No? Okay, good. All right, so if those are reactions, we can figure out what our shear moment diagram are, right? And I haven't put in any loads in here because I know, one, we're going to go through and we're going to calculate what our stress is based on a given load. But then we're going to come back and they're going to give us allowable stress, and then we're going to have to figure out what the allowable load is. And so I'm going to calculate the shear moment diagrams with respect to this uniform load magnitude, okay? So the reactions are W12 over 12, or W12 over 2, essentially meaning we have W6, right? So if we have W6 as our reaction, that means at our reaction we're going to jump up in our shear diagram the magnitude of our reaction, right, which is W6. We have no applied external forces from that point until we get to the uniform applied load, right, 6 feet over. So it stays constant until then, and then we hit this uniform load. It is constant in magnitude. We know based on our rules that the slope of the shear diagram is the magnitude of the uniform load, right? So we know it's going to start at W6 and it's going to travel at a negative slope because our applied load is vertical downward, the magnitude of our uniform load. So by the time we get to 12 feet, we're going to have dropped W12, right? So now we're at negative 6W. And we're at negative 6W. We're going to be constant until we get to the end of the beam where we have our reaction, which is also 6W, this time acting upward. So it's going to bring our shear diagram back up to 0, which we want, right? Shear diagram is 0. Well, if we look at our moment diagram, if our shear diagram is linear, our constant, our moment diagram is linear, it's going to do something like this. We know the magnitude of that is just the area under the shear diagram. So we've got W6 times 6, right? Next portion. Right? Our additional moment is going to be the area underneath that shear diagram. We know that because it's linear, shear diagram is linear, the moment diagram is going to actually be a quadratic, the second order. So it's going to start out steep and it's going to reduce until we get to the center. It's going to be maximum where our shear diagram is 0. Right? And we're going to no longer be adding or subtracting moment. Here we have 1.5 times W6 squared. Right? Essentially, we're adding half the area that we had right here, which is W6 squared. So 1 W6 squared plus half of W6 squared is 1.5 W6 squared. Right? Then we crest over and we go down negative, and then we go back down to 0, right? Close at 0. Same amount of area above and below our shear diagram, which means that we're going to rise and fall the same amount with respect to moment, which is what we should expect based on having simply supports, right? We're assuming there's 0 moment, which is good. All right. So now that we have our internal forces figured out, we figured out M. We need to know what I is, Y is, right? And this modulus ratio. Well, modulus ratio is what we really need to know first. E original, E reference. Well, I'm going to change steel, which is my original, into wood, which is 30,000 over 1,800, 16.67 is our modulus ratio. T originally was 1/2 inch. If we go back to the problem statement, right? So this is T. We know we can't change the depth of our member again, right? Because changing the depth starts screwing around with our strains. So we just got to change the width because we're ultimately trying to change the area.
And so if we're changing the width, we're gonna take our T, that was the thickness of our steel plates, right? And we're gonna amplify them by this modulus ratio.
So now we're going to change it into T reference, or thickness in the wood, is N times the original, right? So we get 0.5 times 16.67, or we get T reference equal to 8.33 inches, okay? So what does that mean? Well, that means our cross-section gets a bit weird. Okay, where this is 8.33 inches. Right? Now this is our steel transformed. Essentially making it into wood, right? And because we only made it wider, we didn't really affect the depth, which the depth is actually 12 inches. And because we didn't affect the depth,
we didn't affect the depth any, right? We made the steel wider. We can't affect the depth, we know that. And so when we go, now we need to know, one is, what's the center of this cross-section? Well, that's pretty easy. It's all one material now, so it's just big one rectangle. Because it's one big rectangle, oh, we don't need that one. I don't know why I drew that. We really want to know this one. All right, our centroid's in the center. Right, it's just one big block of wood at this point. So we know our moment of inertia is BH cubed over 12. B, well, that's, I think each one of these is 3 inches. So it'd be 14.33 inches times 12 cubed, right? That's the height divided by 12. So we get a moment of inertia now equal to 20.64 inches to the fourth. Quite a bit easier than our T section, right? That we transformed before. Because of symmetry, now we just have this rectangular block. Centroid was easily found. We didn't have to worry about doing summation a sub I, y sub I over a sub I. And then figuring out our moment of inertia, again, is easy. We don't have to use the parallel axis theorem. We just have one big block of wood. Okay. So, knowing that, we now have our moment of inertia, our modulus ratio. We really need to figure out what y is. Well, in our case, our y max is equal top or bottom of each of our materials, right? Because they're centered. So our y max could be positive or negative. Okay. So if we go back through here and we start looking at wood, negative m, well, we said it was 1.5 w times 6 squared, 400 pounds per foot times 6 feet squared. I'm going to change
inches to feet. As I mentioned, this could be our Y max. Could be positive or negative, right? We could go to the top of our beam or the bottom of our beam. The distance is the same. Divided by our modulus of elasticity, or sorry, the moment of inertia for our entire cross section. We get maximum stress in the wood is plus or minus 753 psi. Essentially just means we can be either in compression or tension, right? We know the steel minus 1.5 times 400 pound per foot times 6 feet squared times 12 over 1 times plus or minus 6 inches times our N ratio, right? 16.67. All divided by 2,064 inches to the fourth. We get stress in the steel equal to plus or minus 12,560 psi. So those are our answers, right? The wood, based on having 400 pounds per foot on this cross section, is going to see 750 psi in compression and tension, right? Bottom surface and top surface. And then the steel is going to see 12,560 psi, right? And that's all based on the fact that steel is 16.67 times stiff as wood, right? So every 1 unit of strain or every little bit of radius of curvature, that steel is carrying a lot more of the load, right? So the stress gets elevated a lot quicker, right? Man, we were so close to being done too. Part B, they ask us, assume that the allowable bending stresses on the wood and the steel are 1,200 psi and 24,000. Now they wanted us to figure out what's the maximum load that can be applied. Well, again, maximum stress, in our reference material is our traditional equation, right? Well, if we switch that and solve for the maximum moment due to the maximum stress, and this is what we would be doing for our wood. Similarly, as we just decided, right, we have this original material, in this case it's our steel. We have to take into account the modulus of elasticity ratio between the two materials. We resolve for the maximum moment. Out of these, right, we have Y max, we have I, we have N, and we have the maximum stress. They gave it to us now. We can figure out our maximum moment, right? Ah, screw it, we'll do it on Wednesday. Don't forget, we've got homework.